All right, so we had already one video in which we looked at the handle attachments for surfaces and attaching cross caps and so on. And the goal at this point is to go back to triangulations and to planar representations and use them to prove the classification of surfaces. All right, so we're gonna start by looking at a baby case, which is like, well, we want to classify two-dimensional manifolds, but let's start easy with one-dimensional manifolds. And the claim is that every compact Hausdorff one-dimensional manifold is triangulable, and it's in fact just homeomorphic to S1, as we'll see. All right, so what is the strategy? The strategy we've used a few times. So first, given any point in our manifold, what we can do is we can find by definition a neighborhood that is basically homomorphic to an open interval. This we call UP, and such that its closure it's homomorphic to a closed interval. Now, since M is compact by hypothesis, then we can in fact cover M by finitely many of these intervals, these UIs. Now, what we may do in order to, what we're going to do basically is like reorder these open sets and cut them up a bit so that they form exactly the edges of our triangulation. The first thing we do is we pick just one of them. Let's call it U1. And well, let's call it, let's take one of them U1, and we set V1 to be exactly the closure of U1. So this is a closed interval. Now, out of all the remaining intervals, we pick another one called U2 such that it intersects U1. And we can look at the following difference, which by construction is a closed set. And now what we can see is there's what can happen. So basically you can have U2 here and U1 comes, and then the rest is basically a closed interval. You can have maybe U1 comes from both sides and what's left is also a closed interval. And you could have that basically U1 goes all the way up, exactly up to the end of U2. And then what's left here would be only 1 point. Or you could have that it goes all the way across, so U2 is basically contained in U1 and then you don't see anything. So yeah, the situation is you see nothing, a point, or a closed interval, but only one closed interval. So in the other cases, it's sort of not very important if we get the empty set or the point, but if we get a closed interval, then basically we just call that closed interval V2. And V2 and V1, they touch exactly at one end or two ends, depending on the situation. Oh, sorry, yeah, one end or two ends, depending on the situation. And what you should see here is that basically we are discard. I mean, like here we must use Hausdorffness, because what could happen is that if we have, for instance, like a line with multiple double points, then U1 could be on one of the sides of the line, U2 could be on the other side, and then the complement would be like basically a discrete collection of points, all the double points or so. So here at this step is where we are using Hausdorffness. And now basically this process runs through, and then we'll get that our manifold is composed of finitely many edges that are basically forming a circle, right? So then that's a corollary. Every compact Hausdorff one manifold, well, is homomorphic to S1. All right, so now let's do a bit of history. So the main ingredient we're gonna use for the proof of the classification of surfaces is the following. It's a theorem of Rado from 1925, and it says basically that every surface that is compact and Hausdorff can be triangulated. So this is the analog in dimension 2 of what we just did, but in fact in dimension 2 it's more involved. It requires understanding carefully closed curves in surfaces. And I mean, we could do this, but we don't have like so much time this course, so yeah, we will skip that result. This result is called the Jordan curve theorem, and it says that any closed embedded S1 in R2, let's say it bounds a disk, and so that's an important ingredient. And it's sort of a bit similar to what happens here by saying that like 2 points bound an interval essentially. Right, so this is one of the main ingredients. And the consequence that we will prove is the following theorem, which is the classification of surfaces, which is by Dane and Heegard. And it's that every compact Hausdorff surface is homeomorphic to one of the sigma g's we showed, so the surfaces of genus G, or some ng prime, where ng prime is the surface that has basically the word generating its planar representation is like a0 squared, a1 squared, all the way up to ag squared. So this is the non-orientable ones. All right, so for a bit of history, so I mean, this is dimension 2, so this provides a complete classification. A natural question, of course, in topology then is like, well, can we go on, right? So let's go to dimension 3. Can we classify three-dimensional manifolds? And what Moyes proved is that, in fact, every compact Hausdorff 3 manifold is triangulable. And in fact, it does admit a smooth structure. So in this course, we're only seeing topological manifolds. So as you may have seen in the latest exercise sheet, these are manifolds built out of out of balls, essentially, by gluing them using homeomorphisms. And a smooth manifold that you may have seen in other courses, like the differentiable manifolds, they are the same, but like here you will be gluing sort of smooth balls using smooth maps. And what is kind of remarkable is that in dimension 2, sort of every topological surface is a smooth surface. Similarly, in dimension 3, every 3 manifold is a smooth manifold. But nonetheless, already in dimension 3 classification is extremely tricky. Although now we understand it much better after Perelman proved the geometrization conjecture, which basically states that there's like, you can chop up a 3 manifold in certain pieces that have like a particular sort of geometric flavor. Basically, in dimension 2, the analogous statement says that there's 3 types of geometries, which are like the geometry of the sphere, so sort of positively curved, the geometry of the plane, which is like flat, and the geometry of hyperbolic space, which is negatively curved. And what Perelman proved is that basically there's, in dimension 3, there's something similar, but the type of geometries you have is, well, it's a longer list. And in particular, one of the consequences was the Poincaré conjecture. So there's no, every simply connected compact 3 manifold is homeomorphic to the 3 sphere. All right, so in higher dimensions, then the business becomes kind of like much more complicated. In particular, in dimension 4, there's like a lot of sort of exotic phenomena. So basically, in the 80s, Friedman was able to show that to explain how to classify topological for manifolds, and he was able to show that very many of them exist. And sort of a bit later, Donaldson showed that most topological manifolds cannot be made smooth, in fact. So yeah, that's kind of like that's sort of the first dimension in which this happens. And what is sort of extremely remarkable, I think this is pointed out later, is that in dimension 4, if you give me a topological manifold, it may happen that, okay, maybe this topological manifold cannot be turned into a smooth manifold, it doesn't admit a smooth structure, or it can also happen that the topological manifold may admit uncountably many distinct smooth structures. This is the case of R4, for instance, as proven by Taubes. But for instance, there's like still like amazing open questions. For instance, like, does this 4 admit more than one exotic structure? This is somehow, in some sense, the question of like the Poincaré conjecture in dimension 4. And this, well, this is worth remarking. So in class, we saw this result saying that there's many CW complexes, at least as many as groups, right? Because every group can be realized, any finally presented group can be realized as the pi1 of a CW complex of dimension 2. And the idea is that basically, once you're in dimension 4, you're able to basically get a CW complex that has pi of dimension 2 that has pi1 equal to G, and basically close it up to a 4 manifold that has the same fundamental group. So again, there's as many 4 manifolds as groups, so it's kind of very hard to understand these. And that's sort of a bit the reason why people in dimension 4 focus mostly on simply connected manifolds. The story sort of keeps going in higher dimensions. So this is a very recent result, which is that in dimension at least 5, there's compact Hausdorff topological manifolds which cannot be triangulated. And well, this was proven in 2012, I believe. But somehow, a bit maybe shockingly, if you hear this for the first time, it turns out that dimension 4 is the worst, like the most exotic behavior somehow. So in higher dimensions, there's like enough space in the manifold that you can do certain manipulations that allow you to sort of say meaningful things about higher dimensional manifolds. But in dimension 4, sort of, it's a dimension big enough to be a bit like difficult to classify things, and at the same time low enough that you don't have enough space to have like fully flexible behavior. This is a bit vague, but yeah, somehow like for some reason, sort of things do turn easier in higher dimensions. And a result I will mention, well, I mean, okay, and maybe like yeah, this is an important result. So in higher dimensions, for instance, like it is true that topological structure, so a topological manifold may admit different smooth structures, but they are always finitely many. Unlike in dimension 4, where we said, for instance, yeah, R4 can have uncountably many structures, smooth structures. So lastly, let me just mention this result. So every smooth manifold is in fact triangulable. And this result we have seen in the Morse theory seminar that some of you may be following. So in general, the idea you have is like a smooth manifold, you can always be triangulated, but not every topological manifold can be triangulated. All right. So let's move on let's do actual math. So let's get to the classification of surfaces after this historic remarks. All right, so as we said, our goal is proving the following result. Every compact Hausdorff surface, sigma, is homeomorphic to sigma g, the surface with genus G, or ng, the non-orientable surface with like the word a0 squared to ag squared. So as we've remarked in class already several times, so the proof goes through by using planar representations, right? So this is basically, we present our surface as a polygon whose boundary edges are labeled by certain symbols a1 to am, and each of these symbols appears twice and either positively oriented or negatively oriented, telling us how to glue them. All right, so the way in which we're going to build these planar representations is by first starting with a triangulated surface. So here we are using Rado's theorem above, that every topological surface can be triangulated. And in order to build a planar representation from the triangulation, we need to understand a bit better how the triangulation looks. So these are the following claims. So if we have a surface, then every edge is contained in exactly two faces. All right. Every vertex has at least valence 3, so at least there's 3 edges that go into that vertex. And lastly, if there's 2 different edges and they share a vertex, then in fact, I mean, they may not share a face by themselves, but there's a sequence of edges such that E0 shares a face with E1 tilde, and E1 tilde also touches the same, the intersection of E0 with E1. E2 tilde shares a face with E1 tilde, and again, they share the same vertex, the vertex that E0 and E1 share, and all the way up to EM tilde, which is E1. Okay, I'll show you a picture in a second. So let's prove this in order. So let's do the picture. So, okay, let's suppose we have an edge that is contained in a single face. Then we have this picture, right? And now if we look at this point and we take a neighborhood, this neighborhood is not like the neighborhood of a point in R2. And that is a contradiction. And we've done this in class. Well, we've done this, this has appeared as an exercise. The way in which you prove this is by removing P. And once you remove P, you see that this neighborhood remains simply connected. In particular, it remains contractible, the neighborhood, but if you remove a point in R2, it does not, right? Because when you remove a point, the neighborhood retracts to S1. All right, so if you have, if this sounds surprising to you, you should for sure do that exercise, this here. then if an edge has 3 faces incident, then what do we have? So here I have the 3 faces, one in blue, one in red, one in orange. And let's take an interior point of the edge. Let's call it P. So if I remove this point, what happens? So on this side, basically I have the face minus this point. Here I have the face minus this point, and here I have the face minus this point. So a neighborhood of P is in fact homotopy equivalent to this sort of thing, like a circle with a handle. And this we have also done in one of the homeworks, I think, or maybe in class. This is homotopy equivalent to a wedge of 2 S1s. So again, this doesn't look very Euclidean, right? Because normally Euclidean neighborhood minus the point would retract 2 S1. And the answer for like more faces is similar. Basically, you will be, in that case, your neighborhood will minus the point will retract to a wedge of basically the number of faces minus 1 S1s. All right, so this is left as a little exercise, and that proves that every edge has 2 incident faces. Now we do the same for vertices. So imagine you have a vertex P and it has valence 1, so there's a single edge incoming. And now we simply get a contradiction due to the nature of triangulations. So you take the vertex P, you take the edge going out of it, you take the face that, I mean, there must be a face, right? That is incident, well, I mean, there must be 2 faces incident to that edge. And now the contradiction is that since there's a single edge coming out of P, then that the face can, I mean, the face must have that edge twice as in the boundary. And that cannot happen, right? Because a face should have 3 distinct edges. All right, the proof for valence 2 is quite similar. So now we have a vertex P, and now we have, let's say, one incident edge E1, and E1, as we showed before, it must have 2 incident faces, F1 and F2. But now the same reasoning works for E2, right? For the other edge incident to P. So that means that F1 and F2 must be incident to both E1 and E2. So again, they share 2 edges instead of 1, and that's a contradiction because of the nature of triangulations. All right, and lastly, let's do the last claim. So we've shown that every vertex has valence 3, and now what we have to show is that if I have 2 edges and they share a vertex, in fact, they are connected by a sequence of faces that also touch that vertex. So how does this work? So we have, let's start by just looking at E0. So I take E0, and it's incident to 2 faces, one of each, right, of E0. And let's pick one of the faces. Well, that face must have another edge that intersects E0 exactly in the vertex point, right? And we can keep going. Now you take that second edge, you pick the other face, and again you find a third edge that now intersects E0, the second edge in E0 cap E1, and you keep going, and you will keep going until the only way for this sequence to stop is that you go back to E0. And this must happen because of compactness. There's only finitely many edges, so at some point you have to stop. And what this tells you is that basically we get to a picture like this. You started at E0, then you find some E1 and they share a face, some E2 tilde, they share a face, maybe some E3 tilde, they share a face. And eventually you will come back and you'll have formed something that looks like a little disk, and it's centered at the point. Now, if you do the same at E1, you'll again form something that looks like a disk, and then these 2 disks intersect at the point. And of course, then this won't be a surface because locally a neighborhood of this, it's disconnected when you remove the point E0 intersected with E1. So the only way to avoid this is that in fact E1 appeared already in this sequence you did for E0. So E1 is one of these E1 tildes, EI tildes, and that's it. So that shows you that, yeah, indeed the configuration must be something like this. You start at E0, you find a face with another edge, a face and another edge, and at some point maybe this one is E1. All right, so that proves the lemma. All right, so with this lemma at our disposal, we may prove one of the main ingredients of the theorem, which is the following proposition: every triangulated, path-connected compact surface admits a planar representation. And what is the idea? The idea is that basically we're just gonna construct the planar representation by gluing the faces of the triangulation. So let me provide the following auxiliary definition that we need for the proof. So we say that an embedding of a polygon P into sigma is a partial planar representation if, well, it's a polygon such that, well, it's embedded, right? So that means that it's a homeomorphism with its image, and every edge of the polygon should map to an edge of sigma, right? So this basically says that P will be a union of faces of sigma, of the triangulation. Now, what we can try to do is basically, given such a partial planar representation, what we want to do is we want to add to it another face of the triangulation, if unless the partial planar representation covers sigma fully, right? And when that happens, I mean, when we eventually get to a planar representation that is surjective, I mean, that will be an actual planar representation and will be done. All right, so let's assume, to get to a contradiction, that we have a partial planar representation that is maximal, which means that it cannot be extended to anything larger. All right, so I cannot attach to it a new face of sigma. Then what is the situation? So then it must be true that f of P0, so the image of our polygon, must be disjoint from any edge that is not contained in it. Right? Because what is the situation? Well, suppose here I have, this is my maximal polygon that I've been able to construct somehow, and here there's some other edge, and this edge intersects our polygon in a point. Then by the lemma above, then there's a sequence of edges and faces that eventually goes from one to the other. But then that means, oh, look, here's a face, and it's literally touching my polygon, so I could just add it to the polygon. And that would contradict the maximality of the polygon I started with. So that means that if I have a maximal polygon, then it must, it cannot touch any other edge. And from that, what it means is that f P0, so the image of the polygon, and its complement, they are both closed sets. Therefore, they are all both open sets, and they form a covering of sigma. So sigma would be not connected. So the only way to avoid this contradiction is to deduce that if a partial planar representation is maximal, then in fact it is the whole thing. The map is surjective, and that means that sigma, that P0 provides a planar representation of sigma as we wanted. All right. All right, so now that we know that every surface admits a planar representation, now what we're gonna do is we're gonna use this information we're gonna simplify any given planar representation until we get to one of the nice ones. And the nice ones are basically the ones for sigma g, so the surface with unit g, or this ng prime. They are non-orientable surfaces. And that will be the end of the proof, right? Because we'll have reduced to these ones, and we know that these ones, we proved it already in class the last day, these are not pairwise homomorphic. All of them are really different surfaces. And we did this by looking at pi1, if you recall. All right, so it's easy to start with the orientable case. So let's assume our sigma is compact, is path connected, and it's orientable. And since it's orientable, recall that the following happens. So if A0 to AM label are the edges, then, well, I mean, we proved above, right, that every edge must be incident to two faces in a triangulation. So that means that all these symbols, each of them appears twice. And additionally, they must appear with opposite orientations, because if they appear with the same orientation, then we showed the previous day that the surface contains a Mobius band, so it's not orientable. Right. So, okay, we're in this situation. Now what we do is, okay, let's pick one of the labels. Let's pick the label, let's call it A0 for simplicity, but okay, one of them, the label that has the two edges closest to each other. Okay, so, and well, there's essentially two situations. The first one is like, okay, they are the ones closest to each other, and in fact they're adjacent. So you see something like this. They must, as I said before, they must appear with opposite orientation. And now what we can do is basically we can glue them like this. You can form this sort of Pac-Man shape. So the two edges approach each other and we glue them. And now we have essentially, we have the same surface, right? Because these are glued. But now the word representing the surface has, well, 2 letters less, right? So, okay, great. So this tells us that we can basically assume that the same symbol never appears twice, like adjacent to each other. And so now let's assume that, okay, that I have two closest labels A0, but that they are not adjacent. So we have something like this, A0, then some word, and A0 again, and again with opposite orientation. And now what we can do is pick any other label A1. And since A0 and A1 were closest to each other, out of all the labels, we know that these, so since A0 and the other A0 were closest to each other out of all the labels, we know that the two A1s cannot be on this side, on the same side. They must be on opposite sides. So the configuration is something like this: A0, some part of the word, A1, some part of the word, A0 inverse, some part of the word, A1 inverse, and some part of the word. So okay, so this is our planar representation, and now what we're gonna do is when I try to start cutting up things, so we get to, well, we get to 4 symbols that are in a commutator form. So how do we do this? So I pick this this curve here. It will be an edge now after I cut along it. So we cut along B, and now we're gonna glue along A1. So when I cut, this part gets here, and this part gets here. All right. So this already has put like the A0 touching B and then touching the other A0, so that's quite good. And now again we pick another curve here, C, and we cut along it, and we glue along A0. And what that does, it gets us to this shape, right? So this part here has passed to here. And now we've already won, right? Because now we have basically something that looks like, well, W1, W2, W3, W4. So this is essentially part of the word that we had before, also in the following exactly the same order as that it did. And now we have minus B, minus C, B, and C, right? So this is a commutator. And we've won, so right, because we've said, well, our surface basically has planar representation, which is, well, basically the word we had before minus these A0s and A1s, plus the commutator. And from our discussion in the previous video, this shows that our surface is homeomorphic to sigma tilde, whatever this is. This is the surface corresponding to the planar representation with this word, and connect some with T2, right? Because we've added this commutator here. And now, since this word is shorter, right? Like the original word had some length, and this has length minus 4, this whole part, then sigma tilde is sort of a simpler surface, and we can apply induction, apply the argument again. So sigma tilde has to be still orientable, right? I mean, this is something that you can read from the word, so it's still true for this smaller word. And that tells us, like, out of induction, that sigma is homeomorphic to, well, to G commutators for some G. So yeah, G is homeomorphic to attaching G handles to S1, which is the same as the surface sigma G, which is the same as the word, as the surface whose planar representation has word, basically G commutators. So that proves the claim. Okay, let's go on to the non-orientable case. So what's the deal? So since the surface is non-orientable, we know that there must exist some edge A such that it appears twice, of course. I mean, it's a surface, but it appears twice with the same orientation, right? Because then this curve will be a Mobius band. Well, a neighborhood of this curve, of this loop, will be a Mobius band. All right, so if we're in this situation, what we can do, and in fact, we did this already in the previous video when we showed that RP, like let's say attaching two cross caps to a non-orientable surface is the same as attaching a one handle. So we do the same cutting. So we cut from the beginning of one of the A's to the beginning of the other A. We cut along it, and then we glue along A. And when we do this, we get exactly this picture, right? So we get, let's do it from here perhaps. So we get B, then because we are here, we identify it again. So we do B again, then we do W minus 1. And then we're here, so we are in fact in this side, so we do W2, and this is exactly what we see. And now this is extremely nice, right? Because then basically we've proven that sigma has a planar representation that is W inverse and W2, W1 inverse and W2, and then B squared. So that means, as we showed in the previous video, that sigma is homeomorphic to sigma tilde, some other surface, direct sum with, connected sum with RP2, right, attaching a cross cap, and sigma tilde is represented by the word W1 inverse W2. All right. And again, now the induction argument is a bit more tricky, because sure, sigma was non-orientable, but we do not know if sigma tilde is non-orientable, because maybe we've deleted all the pairs that go in the same direction. So this may actually be orientable. So the way this works is basically we take sigma and we keep removing all the pairs that have the same orientation using this argument. So eventually you get to M connected sums of RP2 with some surface that is orientable now. But now we can apply the first step and we say, well, in fact, what is, well, sigma tilde tilde is just good old sigma G. And now we recall, well, this surface is non-orientable and we are attaching to it G handles. So this is the same as attaching to it 2G cross caps. So this surface is in fact, well, M plus 2G cross caps. So it's this surface, NM plus 2G minus 1. So here, recall, this is the important result that we already saw in the previous video. All right, and that is the end of the classification of surfaces. I recommend that you go back to all these cutting and pasting procedures and well, try to do them yourself or so. And basically this wraps up our study of surfaces. So what we'll tackle next is we'll basically start a new topic called covering spaces, and this basically will explain to us how to relate, it will explain how the fundamental group is related to a certain covering property for spaces. This is a bit vague, but okay, we'll see in the next video. And yes, again, please do post your questions on Blackboard. Bye, take care.